Alright, so in this stream, we are going to review Notebook 5th of the FastAI Deep Learning for Coders course. So I have already reviewed up to this portion, and in this stream, we are going to start with model interpretation. So what's model interpretation? It's very hard to interpret loss functions directly because they are designed to things computer can differentiate and optimize, or things that people can understand. That's why we have metrics. These are not used in the optimization process here, I know that, but just to help us poor humans understand what's going on. In this case, our accuracy is looking pretty good already. So where are we making mistakes? Confusion matrix. Okay. So in case of pet breeds classification, we have in total 37 different breeds of pet, which means the confusion matrix gets much more complicated, and it is very hard to determine from this image. So we can use this function most confused. We can use the most confused method, which just shows us the cells of the confusion matrix with the most incorrect prediction. Alright, so it is saying the most confused classes, pair of classes are American Pit Bull Terrier and Staffordshire Bull Terrier. So it's over here. So as you can see, it is the most confused with 10 of the images of Pit Bull. American Pit Bull Terrier are classified as Staffordshire Bull Terrier. So that is the most confused pair. And after that we have Ragdoll and Berman. Right, let's Google these two categories and see what they look like. Alright, so these are the images of American Pit Bull Terrier. And let's also look at the images of Staffordshire. So they look almost similar. They have the same facial structure. No wonder our model is interpreting them as incorrectly. In case of Staffordshire though, most of them are in plain color, like they don't have patches. This one has patch over here, but in case of American Pit Bull, there are many patches on their heads. This dog has patch, this dog has patch. These are in solid color. So we can say that this pair is also confusing for humans as well. Let's also Google ragdoll and Brahman. Okay, so the ragdoll and Brahman cats also look very similar, very much similar. That's why our model is confusing these pairs. Let's check American Bulldog as well, because American Pit Bull Terrier is confused with American Bulldog as well. So the Bulldog looks similar to Staffordshire and Pit Bull as well. As you can see, I have already reviewed up to this code. Let me also run this cell. There's nothing interesting about these two lines of code, so I'm not going to break it down further to investigate what it does. It basically plots the confusion matrix, so that's it. So let's say in the model I trained, which are the most confused breeds. So in my model as well, Staffordshire Bull Terrier and American Pit Bull Terrier, they are classified incorrectly. In our model, we will now look at a range of techniques to improve the training of our model and make it better. Doing so, we'll explain a little bit about transfer learning and how to fine-tune our pre-trained model as best as possible without breaking the pre-trained gates. The first thing we need to set when training a model is the learning rate we saw in the previous chapter. It needs to be just right to train as efficiently as possible. So how do we pick a good one? Right. One of the most important things we can do when training a model is to make sure that we have the right learning rate. If our learning rate is too low, it can take many walks to train our model. Not only does this waste time, but it also means that we may have problems with overfitting, because every time we do a complete pass through the data, we give our model a chance to memorize it. So let's make our learning rate really high, right? Sure, let's try that and see what happens. They have tried 0.1 learning rate, so By giving the parameter base LR, we can tune the learning rate. Let's try to do that. Let's get the CNN learner, pass the data loader class, and resonate 34 architecture, and matrix. For matrix we will pass the error rate. Let's fine tune it just for one epoch. Let's keep the base learning rate as 0.1. Let's check what is the default learning rate. Okay, so the default learning rate is 0.002, so it is lower, and 0.01, 0.1 is higher. Let's try to fine tune it. So the error rate increased when we increased the learning rate because it started overshooting. The figure for overshooting is given in this notebook, I guess. Okay, so it's this one. And so this is what is happening when we increased the learning rate. It started to get worse and worse. The loss started to increase instead of decreasing because we are taking bigger steps. If we take a bigger step, then it moves from one slope to another, to the opposite slope. If we keep it very much slower, very much lower, if we keep the learning rate lower, then it takes a lot of steps to get down to the local minima. These two images are almost similar, I guess. And in both of these cases, the loss gets worse and worse. Doesn't look good. Here's what happened. The optimizer stepped in the correct direction, but it stepped so far that it totally overshot the minimum loss. Repeating that multiple times makes it further and further away, not closer and closer. Further and further away, not closer and closer. Alright. What do we do to find the perfect learning rate? Not too high and not too low. So we are trying to optimize this parameter, learning rate. In 2015, the researcher Leslie Smith came up with a brilliant idea called the learning rate finder. This idea was to start with a very small learning rate, something so small that we would never expect it to be too big to handle. Alright, our model is done fine tuning. So this model has also overshoot the the error rate didn't improve, but it actually got worse from 0.82 to 0.93. It got worse than this model. So let's try to find out the optimum learning rate. His idea was to start with a very small learning rate. Something small that we would never expect it to be too big to handle. We use that for one mini batch. Find what the losses are afterwards and then increase the learning rate by some percentage. That is doubling it each time. So we incrementally increase the learning rate batch by batch. Then we do another mini batch, track the loss and double the learning rate again. We keep doing this until the loss gets worse instead of better. This is the point where we know we have gone too far. We then select a learning rate a bit lower than this point. Our advice is to pick either one order of magnitude. One order of magnitude less than where the minimum loss was achieved. That is the minimum divided by 10. The last point where the loss was clearly decreasing. The learning rate finder computes those points on the curve to help you. Both these rules usually give around the same value. In the first chapter we didn't specify a learning rate using the default value from the FastAI library, which is 1 e raised to minus 3. 1 e raised to minus 3 means 0.0001, right? Yeah, it is 0.001. 10 raised to minus 3. Right, so FastAI library provides a function called lrfind to find the learning rate. Let's try to run it. Learn TLS ResNet 34 metrics error rate. It gives us two values in return: LR minimum, the minimum learning rate, and the learning rate steep, where it is most steepest. Does this steep, okay, learning rate with at the steepest point is equal to learn dot lr find. This lr find function is provided by schedule.py. Okay, so it is from the FastAI library. So this graph plots it, the loss versus the learning rate. So for the first batch, we are selecting a very minimum learning rate, and as the batch size, as we move on to another batches, we are incrementally increasing the learning rate. It is said over here that we are doubling it each time. So as we are doing that, after some times the loss starts to get lower and lower until it reaches a point after which it starts to get worse again. So this is the minimum loss. What this function returns is LR minimum and LR steep. LR minimum is 10 raised to 1 e raised to minus 2 means 0.01, which could be this one, 10 raised to minus 2, or could it be this one? Because the minimum, it is said that this function returns the minimum divided by 10. So if the minimum is 10 raised to minus 1, then it returns this point divided by 10, minimum divided by 10. So this 0.01, and the steepest point is 0.00005, which could be somewhere around here, I guess. So it is somewhere around here. So the optimum learning rate lies between this point and this point. So we should pick from this range. One zero zero eight. So it is similar to the notebook. Okay, and we can see that on this plot that in the range 10 raised to minus 6 to 10 raised to minus 3, nothing really happens. From this point up to this point, nothing really happens. The loss is almost flat and the model doesn't train. Then the loss starts to decrease until it reaches a minimum up to this point, minimum, and then increases again. We don't want a learning rate greater than 10 raised to minus 1. Yeah, we don't want this learning rate because because our model gets worse if we choose something from this range, as it will give a training that diverges like the one before. You can try for yourself. Point, we tried point one, so it lies over here. Point one. What if we increase it again? Then it will get much worse, I guess. And let's not try it. But yeah, it is already too high. Yeah, this learning rate that we used was already too high. At this stage, we have left the period where the loss was decreasing steadily. We have left this period. In this learning rate plot, it appears that the learning rate around 3 e raised to minus 3 would be appropriate, somewhere around this range. So let's choose that. Alright, let's choose that. Let me directly copy this line of code. Learn.find new. Let's now try to train it for 2 epochs and keep the base learning rate 3 e raised to minus 3. Logarithmic scale. The learning rate finder plot has a logarithmic scale, which is why the middle point between 1 e raised to minus 3 and 1 e raised to minus 2 is between 3 e raised to minus 3 and 5. This is why we care mostly about the order of magnitude of the learning rate. This is because we care mostly about the order. What is it saying? This plot is for the logarithmic scale. So this is the logarithmic value of this. Does it mean that? Let's try to find log of this value. Log of minus 1.70. This is not a log. What if it is a natural log or something? Is this a natural log? Oh, I don't know. Minus 1.90. Minus, why is it minus? Why is it negative? What does the logarithmic scale mean? Numeric data over a very wide range of values in a compact way. Typically, the largest number in the data are hundreds or even thousands of times larger than the smallest number. Since the scale is non-linear, the numbers 10 and 20 and 60 are not the same distance apart on a log scale. Plot of internet host count over time on a logarithmic scale. Okay, so in essence, it is used for displaying numeric data, which contains very wide range of values. Okay, we don't get it. Suppose if we were to use this method, this function learning rate finder, and it gives us this learning rate, minimum learning rate, and steepest point is this. Now if we were to choose an optimum learning rate, how are we going to choose it? They are not showing us how to calculate this 3 e raised to minus 3 from this range. Do we take log of this? Let's Google it. Learning rate finder. Someone has already asked this question. Choosing the learning rate using FastAI LR fine. Okay, this person is asking the exact question that we are asking. The idea for learning rate range test as done in LR fine comes from this paper that has a lot of useful tuning tips. It's worth studying closely. So it's talking about this paper, cyclical learning rates for training neural networks by Leslie and Smith. If in LR5 the learning rate is slowly ramped up in a log linear way. You don't want to pick the point at which the loss is lowest. You want to pick that at which is stopping faster per step. Though it does happen somewhere around the middle, or so the guy wrote, has it about right. Anything between e raised to minus 2 and 3 raised to minus 2 has roughly the same slope and would be a reason. So is the smaller values would correspond to a bit slower. I'll try to again so learning rate is equal to what this reading is steps. Okay, we know this much. He's saying that in this notebook which he is referring, the author passes 1 e raised to minus 2. So he directly passes the logarithmic learning rate. But in this case, the author passes this values instead of this range, values from this range. How do we get this range out of this range? What kind of logarithmic function should we apply it? 1 e raised to minus 3 Let's just roll with it. We will see it later maybe. Let's read further. It's interesting that the learning rate finder was only discovered in 2015. While neural networks have been under development since the 1950s. Throughout that time, finding a good learning rate has been perhaps the most important and challenging issue for practitioners. The solution does not require any advanced math and computing resources. Usually does require anything else that make it inaccessible to any curious researcher. Furthermore, Leslie Smith was not part of some exclusive Silicon Valley lab but was working as a naval researcher. All of this is to say breakthrough work in a plus deep learning absolutely does not require access to vast resources, select teams, or advanced mathematical ideas. There is a lot of work still to be done that requires just a bit of common sense, creativity, and tenacity. Now that we have a good learning rate to train our model, let's look at how we can fine-tune the weights for pre-trained model. So our model is done fine-tuning, and this time we are getting 0.24 error rate. So the base learning rate is optimum. Let's move on. I would also like to review this paper. It would be fun to read it and figure out how they are calculating this this base learning rate from the logarithmic rate. That's for later, but let's focus on this topic right now. Unfreezing and transfer learning. We now know that a convolutional neural network consists of many linear layers with a non-linear function. Okay, between each layer followed by one or more linear layers with an activation function, such as softmax at the very end. Final layer uses a matrix with enough columns such that the output size is the same as the number of classes in our model. The final layer uses a matrix with enough columns such that the output size is the same as the number of classes. So in case of pets and pet breeds, we have in total 37 classes. So the outermost layer should be of size 37. Can we check it? Let's check it. Learn dot model. Let's check what is inside learn.model. Alright, we have the whole architecture, and if we check the last layer, linear output features are 37. So 37, we have the output features 37. So the outermost layer is of size 37. It is the same number as the pet breeds. This final linear layer is unlikely to be of any use for us when we are fine tuning in a transfer learning setting, because it is specifically designed to classify the categories in the original pre-training dataset. All right. So in the original pre-training dataset, suppose there were 50 categories. So that final layer was used for classifying those 50 categories. So it is said over here that this layer is not necessary because it is not apt for our use case, because we don't want to classify 50 categories. We want to classify 37 categories, and those final layers are fine-tuned for those 50 categories. So when we do transfer learning, we remove it. So in case of transfer learning, we remove it. We remove the last layer, throw it away, and replace it with a new linear layer with the correct number of outputs for our desired task. In this case, there would be 37 activation for 37 categories. This newly added linear layer will have entirely random weights. Alright. For our model prior to fine tuning has entirely random outputs, but that does not mean that it is an entirely random model. All of the layers prior to the last one have been carefully trained to be good at classification, image classification task in general, as we saw in the images from Zeidler and Fergus paper. Okay, now we want to train a model in such a way that we allow it to remember all of these generally useful ideas from the pre-trained model and use them to solve our particular task. So they say remember all these general useful ideas. They mean like the features like eyes and eyes, nose, gradients, vertical lines, horizontal lines, and all of those generalized features which we can use to classify pet breeds as well, and only adjust them as required for the specifics of a particular task. Our challenge when fine-tuning is to replace the random weights in our added linear layer with weights that correctly achieve our desired task, classifying pet breeds without breaking the carefully pre-trained weights and other layers. So challenge is to not touch the pre-trained weights and other layers, only touch fine-tune the last layer that we add. There is actually a very simple trick to allow this to happen. Tell the optimizer to only update the weights in those randomly added finally. the optimizer to only update the weights in this randomly added final layers. Don't change the weights in the rest of the neural network at all. This is called freezing those pre-trained layers. All right. And when we create a model from a pre-trained network, FastAI automatically freezes all of the pre-trained layer first. So the CNN learner already does the freezing of those pre-trained layers. When we call fine-tune method, FastAI does two things. This fine-tune method, let's open up the source code for fine-tune. Trains the randomly added layer for one epoch with all other layers frozen. So first it freezes all the layers that are from the pre-trained. It freezes all the pre-trained layers and it hits one cycle. Trains a randomly added layer for one epoch. So it fits one cycle for freeze epochs, which is one slice baseline, right? Okay, and unfreezes all of the layers and train them all for the number of epochs requested. So after it is done training the final layer for one epoch, it also divides the base learning rate by 2 and unfreezes all the other layers as well and fits all the layers of our model for the epochs that are specified in the function. Okay, although this is a reasonable default approach, it's likely that a particular dataset may get better results by doing things slightly differently. What does it mean, slightly differently? The fine-tune method has a number of parameters you can use to change its behavior. These are the parameters provided by the fine-tune method. But it might be easiest for you to just call the underlying methods directly if you want to add some custom behavior. Then in this underlying methods, freeze and unfreeze and fit one cycle. Remember that you can see the source code. Yeah, we have already opened the source code. Let's try to manually do the fine tuning. First of all, we train a randomly added layer for 3 epochs using fit one cycle. So when we call fit one cycle, it only trains the randomly added layers. Does it mean that CNN learner already freezes the previous layers? Because if we call fit one cycle directly, then doesn't it train all the layers? Let's also check the source code for CNN learner, sorry. So this is the source code for CNN learner. CNN learner, what does it do? CNN learner calls another function, learner. So we have to check the source code of learner now. In the lecture, in the course, Jeremy does say that CNN learner freezes the model, freezes the previous layers. Alright, so let's take it as given that CNN learner freezes the previous layers. That has to be the case because after doing one cycle, we are calling the unfreeze method. So maybe this CNN learner does freeze the previous layers. Now let's try to fit it for one cycle. We are only running the randomly added layers for 3 epochs, and the learning rate is 3 e raised to minus 3. We are done fitting for one cycle. We unfreeze the model and run LR500 because having more layers to train and weights that have already been trained for 3 epochs means our previously found learning rate isn't appropriate. Okay, having more layers to train and weights that have already been trained for 3 epochs. So after doing unfreezing, we have to call LR fine again. But in this case, we called it directly after the CNN learner. Model has been trained, but this giving us 0.23 error rate. Like, still not there yet. Learn dot unfreeze. Call unfreeze method now and unfreeze the retained layers. And now we have to find the learning rate. Graph is a little different from when we had random weights. We don't have that sharp decision that indicates the model is training. So this graph was when we had random weights. So when we call the CNN learner on the data set again and get the learner, we are again getting the randomly assigned weights. So in that case, the graph was something like this. And in this case, when we train it for one cycle, when we freeze the layers, pre-trained layers, train it for one cycle and unfreeze it and find the learning rate, it is different. That's because our model has been trained already. Our model has been trained. The pre-trained layer were trained. The pre-trained layer are already trained, and also we have trained the random weights for one cycle for 3 epochs. So that's why we are getting almost flat loss for this range of learning rate, and then starts to overshoot. Here we have something flat, somewhat flat area because of sharp increase, before a sharp increase, and we should take a point 12 before that increase. We should take something from this range, I guess. E is to minus 5. This is taking it from this range. Also have to take, we can also take the similar range. The point with the maximum gradient isn't what we look for here. This point. Okay, now let's train all the layers for 6 epochs and LR-max. Why are we passing LR-max? In this case, we are passing. What's the difference between LR-max and base LR? We were providing base LR to the fine-tune method, and for the fit one cycle, we have to pass LR-max. Alright. While we are there, let's also check the source code of fit one cycle. So it has LR-max variable. Okay, let's train it for 6 epoch. This has improved our model a bit, but there's more we can do. The deepest layer of a pre-trained model might not need as high a learning rate as the last ones. So we should probably use different learning rates for those. This is known as discriminative learning rates. even after we unfreeze, we still care a lot about the quality of those pre-trained weights. We would not expect that the best learning rate of all those pre-trained parameters would be as high as for the randomly added parameter. So yeah, we don't need the learning parameter for those pre-trained model as high because they are already trained. We don't want to tweak them as much as the final layers, right? Even after we have tuned those randomly added parameters for few epochs. Remember, the pre-trained weights have been trained for hundreds of epochs on millions of images, of course. In addition, do you remember the images we saw? Therefore, FastAI's default approach is to use discriminative learning. Okay, this was originally developed in the all-in-fit approach to NLP transfer learning that we will introduce. Top one, accuracy, higher is better. Layer n at which network is chopped and retrained. What is this saying over here? Transfer plus fine-tuning. Transfer plus fine-tuning improves generalization. That's what we did. Fine-tuning recovers co-adapted interaction. It recovers co-adapted interactions. What does it mean? Co-adapted interactions. And performance drops due to fragile co-adaptation. Performance drops due to representation specificity. FastAI lets you pass a Python slice object up anywhere that a learning rate is expected. The first value passed will be the learning rate in the earliest layer of the neural network, means the pre-trained layers, and the second value will be the learning rate in the final layer. Okay, and the layer in between will have learning rates that are multiplicatively equidistant throughout that range. Let's use this approach to replicate the previous training, but this time we will only set the lowest layer of our net to a learning rate of 1 raised to minus 6. The other layers will scale up to raised to minus 4. Our previous model is still learning. Learn is equal to CNN learning. In the data set, the resonate 34 matrix will remain the same as well. At the rate, now we are fitting it for one cycle. For 3 epochs, and we pass 3 raised to minus 3 as the learning rate. Then we unfreeze the pre-trained models, and once again Fit it for one cycle. Fit one cycle for 12 epochs, and now we are passing a slice instead of a scalar value. We are passing 1 e raised to minus 6 to 1 e raised to minus 4. What does this slice function do? Slice method. Slice Python. Slice object. Returns a slice object. A slice object is used to specify how to slice a sequence. You can specify where to start slicing and where to end. You can also specify the step. So we are passing this value for the starting value, and this as the ending value. The step size is default to 1. We pass the slice, it is passed over here. Set optimize set hyperparameter self.lr if lr max is none, else lr max. So it is calling this function in return offset hyperparameter. When we didn't pass the discriminative learning rates, we were getting 0.059 as the error rate, and when we pass the discriminative learning rates we are getting 0.054. So we did improve the model. I guess it was 0.59, 0.059, and it is 0.054. But we, in this case, we are also training it for 12 epochs instead of only 6 epochs. Training and validation loss. What does the x-axis represent? The y-axis is for the loss, but x-axis is for it. It start from 0 to 10, 1000. As you can see, the training loss keeps getting better and better, but notice that eventually the validation loss improvement slows. It slows over here, and sometimes even gets worse over here. This is the point at which the model is starting to overfit. In particular, the model is becoming overconfident of its prediction, but this does not mean that it is getting less accurate necessarily. Take a look at the table of training results per epoch. You will often see that the accuracy continues improving even as the validation loss gets worse. It gets worse after this epoch, 80, 86, 81, 81. But the error rate is also getting worse. It goes from 51 to 54. The loss is just a function we have given the computer to help us optimize. Another decision you have to make when training the model is for how long to train for. I will be back in a bit, guys. Hello, Lumjacker. How are you? Right, so previous model has been trained and we got 0.19 error rate. Selecting the number of epochs, and another decision we have to make when training the model is for how long to train for. We will consider that next. Selecting the number of epochs. Okay. Often you will find that you are limited by time rather than generalization and accuracy. Choosing how many epochs to train for, so your first approach to training should be simply to pick a number of epochs that will train in the amount of time that you are happy to wait for. Then look at the training and validation loss plots as shown above, and in particular your metrics, and if you see that they are still getting better even in your final epochs, then you know that you have not trained for too long. So in this case, or rather in this case, when we trained it for 11 epochs, uh, the accuracy started getting a little bit worse after the 8th epoch. So it stopped at 0.051 and it started decreasing again. So I guess we can just train it for 8 epochs. That will be the sweet spot. On the other hand, you may well see that the matrix you have chosen are really getting worse at the end of training. Yeah, he's talking about this 3 epochs. Remember, it's not just that we are looking for the validation loss to get worse, but the actual metrics. Yeah, the actual metrics. This error rate is the actual metric, and your validation loss will first get worse during the training because the model gets overconfident, and only later will get worse because it is incorrectly memorizing the data. We only care in practice about the later issue. incorrect. We care about it not being incorrectly memorizing the data. Okay, so how do we prevent our model from incorrectly memorizing the data? Remember, our loss function is just something that we use to allow our optimizer to have something can differentiate and optimize. It's not actually the thing we care about. Before the days of one cycle training, it was very common to save the model at the end of each epoch and then select whichever model had the best accuracy out of all the models saved in each epoch. Before the days of one cycle, they mean this one cycle. Save the model at the end of each epoch. This is known as early stopping. However, this is very unlikely to give you the best answer because those epochs in the middle occur likely to give you the best answer because those epochs in the middle occur before the learning rate has had a chance to reach the small values. Okay, it means this range. The learning rate doesn't get a chance to reach the small values. Wait, we start from the small values. Okay, it means they mean this thing. As the loss, as we reach to the local minima, the learning rates get smaller and smaller, right? The gradients get smaller, I guess. And then to see it over here that, however, this is very unlikely to give you the best answer because those epochs in the middle occur before the learning rate has had a chance to reach the small value. Okay, where it can really find the best result. So we know that we can find the best results after a few more epochs. And what does this mean? The learning rate has had a chance to reach the small values. We are not changing the learning rate during an epoch, do we? We are changing this learning rate as we move from the earlier layers to the final layer. Okay, right. Therefore, if you find that you have overfit What you should actually do is retrain your model from scratch, and this time select a number of epochs based on where your previous best results were found. So in this case, previous best results were found during the 8th epoch. So we should train it for 8 epochs. Train this model for 8 epochs. If you have the time to train for more epochs, you may want to instead use that time to train more parameters. That is, use a deeper architecture. In general, a model with more parameters can model your data more accurately. There are lots of caveats to this generalization, and it depends on the specifics of the architectures you are using, but it is a reasonable rule of thumb for now. For most of the architecture that we will be seeing this book, we can create larger version of them by simply adding more layers. However, since we want to use pre-trained models, we need to make sure that we choose a number of layers that have already been pre-trained for us. This is why in practice architectures tend to come in small number of variants. For instance, the resonant architecture that we are using in this chapter comes in variants with 18 layers, 34, 50, and 101 and 152 layer pre-trained on ImageNet. Okay, and a larger, more layers and parameters, sometimes described as the capacity of a model. Version of resonant will always be able to give us a better training loss, but it can suffer more from overfitting because it has more parameters to overfit with. So in case of layers also, we have to find a sweet spot for our use case. And in general, a bigger model has the ability to better capture the real underlying relationships in your data, and also to capture and memorize the specific details of individual images. So as the layers, as with the architecture gets deeper and deeper, it can find different relationships, very detailed relationships. It can find the features that the dense, not so dense layer can't find. However, using a deeper model is going to require more GPU, of course. So you may need to lower the size of your batch to avoid an out of memory error. This happens when you try to fetch too much inside of your GPU and looks like. So previously I tried to use a ResNet 50, I guess, in one of the models. So I think I tried to use ResNet 50 in this model only, and it did give me this error, runtime error, CUDA runtime error, out of memory. So whenever this happens in this notebook, we have to restart the notebook. You may have to restart your notebook when this happens. Yes. And the way to solve it is to use a smaller batch size, which means passing smaller group of images at any given time through your model. So I guess the batch size is 64, or is it 32? Let's check the source code of CNN Learner. I guess it is 32. The batch size should be 32, the default batch size, I guess. When I try to train with Resonix 50 also, I tried to minimize the batch size, but it was still giving me CUDA runtime error. I guess because the free version of Google Colab doesn't provide that much memory to train on larger datasets or dense architectures. It is sufficient just for this kind of toy problems, I guess. Maybe not. Maybe we can fine tune other parameters to fit inside this memory. Okay, so the base wallet is smaller batch size, which means passing smaller group. You can pass the batch size you want to go to the call, creating your data loaders with BS. Okay, so we have to set the batch size inside the data loaders. Let's check the data loaders function. It was somewhere around here, I guess. Yeah, this we have to pass the batch size to this function. As our model is training right now, it is not showing us the pop-up menu for this function. Let's try to check the source code in the FastAI library itself. FastAI data loaders. Data loaders. So it is over here. BS is equal to none. So BS, the default is none. What does it mean? If it is none, then it is assumed that get item returns a batch. What does that mean though? It uses when it is none, data set dot get item returns. So it is assumed that this get item returns a batch. Get item. Okay, so it is assuming that get item, is it referring to this parameter or what? Does it mean that in this case it is using the whole of, no, it can't be, the whole data set. So the default batch size is none. Is this what this documentation is trying to say? The default is none, then it is assumed that the dataset dot get item returns a batch. Dataset dot dataset this dataset. So dataset is this path. Okay, data set is written by this data block get items, get image file, but that get image file, it returns all the images. The other downside of deeper architecture is that they take quite a bit longer to train. One technique that can speed things up a lot is mixed precision training. This refers to using less precise numbers, half precision floating point, also called FP16, where possible during training. FP16. So we are writing these words in early 2020, nearly all currently, and we GPU support a special feature called tensor cores that can dramatically speed up neural network training by 2 to 3x. They also require a lot less GPU memory. To enable this feature in FastAI, just add to FA16 after your learner creation. You also need to import the module. Which model? This model called back to FA16. You can't really know ahead of time what the best architecture for your particular problem is. You need to try training some. So let's try a resonate 50 now with a mixed precision. Okay, we have to train another model. I'm not done training the previous model yet, and now we have to train another model. But if we check these results from the notebook, this model takes 26 and this model takes 25, so it is almost same. And given that this model is trained for a denser architecture, which is the resonate 15, and the previous model was trained using resonate 32. So this method does improve the time. You will see here we have gone back to using fine tune. Since it's so handy, can pass free epochs to tell FastAI how many epochs to train for while frozen. It will automatically change learning rates appropriately for more dataset. In this case, we are not seeing a clear win from the deeper model. It is useful to remember vehicle models aren't necessarily better for a particular case. Make sure you try small models. So the accuracy didn't improve very much. It is almost, I guess, similar. It is 0.054, and we were getting the similar accuracy using resonate 34 as well. So the model didn't improve that much by using a denser architecture. In this chapter you learn some practical. Okay, this is it for this notebook. Given the questionnaire, and for further research they are asking us to rate the paper. This paper, they are asking us to rate the paper cyclical learning rate for training neural network. See if you can improve the accuracy of the classifier in this chapter. What's the best? So in the previous stream I tried to create a chess-based image classifier, and now that we have learned some few more tricks like discriminative learning rates and learning rate finder, we will use these techniques in the next stream maybe. to improve our chess-based image classifier. And I guess we don't need to train this model. We already know what it is going to look like, so we shouldn't really waste time. So yeah, this is it for this stream. I will see you guys in the next stream. Bye.